Hello, now we move on to the advantages of a negative feedback. We have looked that negative feedback has only one disadvantages, which is the gain will be reduced. So now we move on to the advantages of a negative feedback. Why it is used instead of we have a very low gain at the output. Okay, so the first advantage is desensitize the gain or better stabilize gain, meaning that the overall closed loop gain will be stable. Okay, actually the gain will be reduced by a factor of 1 plus beta A. We have derived this equation AF equals to A divided by 1 plus beta A. The gain is reduced, which is the disadvantage. But the advantage is, if you look at this equation, 1 plus beta A. Okay, beta A is usually greater than 1. So if I ignore 1 over here, I can write this equation as A divided by beta A. A at the numerator, A at the denominator cancel out. So I left with AF equals to 1 over beta. What does this mean is your overall gain AF is just depends on the feedback network. It doesn't depend on the amplifier being used in the circuit. The A is not there. So it just depends on the beta. And usually the beta, which is the feedback network, consists of just a resistor. Resistor is very stable element in electric circuit. Okay, so that's why we use a negative feedback even though the gain is reduced, but the circuit is more stable. For example, if you look over here, this is a circuit without a feedback. So I have a source over here, Vs, and since there is no feedback, my Vs is equals to Vs over here. So what is my Vo? My Vo is simply the input, which is Vs, multiplied with A. You amplified the signal. Okay, so Vo is equals to AVI or A equals to AVS. Suppose that your amplifier over here has a gain of 200 and your Vs over here is 1 volt. So your Vo using this equation will be simply the gain 200 multiplied with the input, which is 1 volt. So you get a 200 at the output, 200 volt. Okay. But now, suppose that this amplifier has been changed to 100. The gain is 100 now. The input is still 1 volt. Your Vo right now will be A multiplied with the input. It is 100. So there is a change of gain from 200 to 100. Your output is also changed from 200 to 100. So there is a 100% change in the output. Okay, due to the 100% change in the gain. Okay, but now the same circuit, but you introduce a negative feedback over here. What will happen to the V out? Okay, so for this particular circuit, I have to find the beta first, and my VF is the voltage signal out of my feedback network over here. It is simply the voltage across R2. Coming to the feedback network is your VO over here. So using a voltage divider, my VF is simply VO multiplied with R2 divided by R1 over R2, which is this equation. Okay. So from there, beta, which is the feedback network over the output signal, VF over VO is beta. It will equals to R2 over R1 plus R2. I have R1 of 9K, R2 of 1 kilo ohm. So if I calculate this, I will get 0.1. This is the value of my beta. Okay. So now, suppose that my gain is 200. What will be my overall gain with feedback, which is my AF? So I can use this equation, A divided by 1 plus beta A. Just use A 200, beta that we have calculated just now, which is 0.1. And I get a gain of 9.52. Of course, the gain will be reduced, which is the disadvantage of having a negative feedback. But suppose that now my gain is 100. If I calculate again the overall gain with feedback AF, it will be A divided by 1 plus beta A. So now A is 100, the beta just now 0.1, and I get 9.09, the overall gain AF with feedback. So if you look over here, from 9.52 to 9.09, okay, the change is only by 4.52%, even though the gain, the overall gain is 200, the individual gain of the amplifier is 200, and then I change it to 100. There's a 100% change from 200 to 100, but the output change is only by 4.52. So meaning that this circuit, which is the one that has a negative feedback, is a more stable circuit because it doesn't depends on the amplifier gain A, but it depends on the value of beta. So that is the advantage of having a negative feedback. Okay, now we look into the second advantage of a negative feedback. So this is the block diagram of a negative feedback. So a negative feedback has a controllable operation. The circuit is more linear in its operation. So how does we show this advantage? Okay, so if you look over here, this is an amplifier, which is my op-amp, in a open loop. There is no feedback. My VO will be simply A multiplied with VD. VD is the difference over here. Okay, so if you look at this equation, the VO depends on the amplifier gain A, the op-amp gain A, which is determined by the manufacturer. We don't have control over that. Okay, and suppose that we use this op-amp in this configuration. In chapter 1, we have learned about inverting amplifier. Vin is coming into the negative terminal. So using the inverting amplifier, you can write your VO is equals to A multiplied with Vin is simply minus RF over R1 multiplied with Vin. So if you look over here, your output voltage depends on the ratio of RF over R1. So we are using a negative feedback, okay, to control the overall gain of this circuit. So this is the second advantage of having a negative feedback. You can control the gain. Next is the third advantage of a negative feedback. It will reduce the effect of noise. Okay, so if you look over here, it will reduce the distortion of the output signal. Okay, noise is unwanted electric signal generated by the either by the component in the circuit or by extraneous interference from outside, but it can be reduced by having a negative feedback. Okay, so how does the negative feedback do that? Okay, so if you look over here, okay, the noise is cancelled because if you look over here, this is the source signal, this is the feedback signal. It is out of phase. Since it is out of phase, it will be cancelled out. Yeah? It is opposite in phase. So that is how the noise is reduced by a negative feedback circuit. Okay, and also if there is a distortion, it is reduced because we remember that AF, the overall gain, is A divided by 1 plus beta A. So since if there is a distortion, the distortion will also be reduced by the negative feedback circuit. So this is the third advantage of having a negative feedback. Okay, now we move on to the fourth advantage of a negative feedback. It will extend the bandwidth of the amplifier, or we say that it improves the frequency response. A frequency response is just a gain versus the frequency of the circuit. So the black curve over here is the overall frequency response of a circuit without a feedback. Okay, you have the maximum gain or mid gain A. At the cutoff, it will be reduced by 30%. Okay, so this is your low cutoff frequency. Similarly, at the high frequency, this is the high cutoff frequency. Okay, so this is without feedback. Suppose you employ a negative feedback, what will happen? The gain will be reduced to AF, because AF is A divided by 1 plus beta A. Of course, it will be reduced, the disadvantage. But if you look over here, the low cutoff will be reduced, the high cutoff will be increased. And with that, your bandwidth is much greater. So this is the bandwidth without feedback, but bandwidth with feedback is longer compared to without feedback. So this is the third advantage of having a negative feedback. Okay, so if you look at the low cutoff frequency just now, the low cutoff frequency will be reduced by a factor of 1 plus beta A. It is FL divided by 1 plus beta A. Okay, it will be reduced. So FL divided by 1 plus beta A. What about the high cutoff frequency? FHF will equals to FH multiplied with 1 plus beta A. So if you look at these two, your high cutoff frequency with feedback is larger compared to the high cutoff frequency without feedback. So FHF is FH multiplied by 1 plus beta A. So this is the relationship between FHF with FH and just now FLF with FL. The cutoff frequency is reduced and the high cutoff frequency is increased. So the overall bandwidth will be increased. Okay, the red one is the bandwidth for the circuit with feedback. Of course, the gain is reduced. Just now I've mentioned that. Okay. So how do I get the relationship between FL and FLF? Okay. We remember that for any circuit, it is a function of frequency. So I can write that A is a function of frequency, which is simply the mid gain or the maximum gain divided by 1 plus JFL over F. This is the transfer function of a circuit. Okay, and we know that with feedback, AF, the A will be divided by 1 plus beta A. So if we apply a negative feedback to this circuit, we can simply write that it is the A is also a function of a frequency. So you substitute AF with this thing over here. A function of frequency, so 1 plus beta A. So this one is this part. Okay, so this is actually A divided by 1 plus beta A. Only that the A over here is a function of frequency. Simplify this equation. Okay, just a mathematical manipulation. Simplify it further. Okay, this one you have to do exercise. How do I get from this equation to this equation? It is just mathematical manipulation. Okay, so from this, if you look over here, I have a function frequency multiplied with 1 plus beta A, and if you look over here, I define AF as AF divided by 1 plus JFLF over F, meaning that the overall gain is a function of frequency. So AF divided by 1 plus JFL over F. So with that, I can write that AF is A divided by 1 plus beta A, which is, we come to the same equation previously, and we get the relationship between FL and FL. Okay, your FLF will be FL divided by 1 plus beta A, because FLF will be less than FL. Okay, and similarly for the high cutoff frequency, any amplifier is a function of frequency and can be written in this form: A maximum or A mid divided by 1 plus JFF over FH. Okay, and we have derived this equation before. AF is A divided by 1 plus beta A. Since A is a function of frequency, so you just substitute this value into this equation. Okay, so meaning that your overall gain with frequency, it is also a function of frequency. Okay, because the A is a function of frequency over here. So plug in this value into this equation. So this is A, 1 plus beta A. Simplify this, okay. It is a mathematical expression. You do some manipulation, simplify it further, okay. So I can write it in terms of this. I just divide everything with 1 plus the value over there, okay. And from there, I can get that AF, which is the overall gain, is a function of frequency. The AF is a function of frequency divided by 1 plus JF over FHF. And if you look between these two equations, I can simply deduce that AF, the overall gain with frequency, is a function of frequency. It will be simply A divided by 1 plus beta A, okay, which is the same equation that we get previously. And the high cutoff frequency will be FH multiply 1 plus beta A. So FHF will be much greater than FH. One thing that you have to know about a circuit that having a negative feedback is about a gain bandwidth product, GBP. Gain is AF, this is the bandwidth. This is gain A, this is the bandwidth. Gain multiply with bandwidth. So that's why gain bandwidth product. Okay. This thing is important because most of the data sheet will give the gain bandwidth product for the amplifier that you use in the circuit. And we know that the relationship between high cutoff, low cutoff with feedback with low cutoff without feedback is FLF equals to FL divided by 1 plus beta A. But for the high cutoff with feedback, it is multiplied with a factor of 1 plus beta A. Okay. For the bandwidth is high cutoff minus the low cutoff. So for bandwidth for feedback, okay, so it is FHF minus FLF. And since FHF is much greater than FLF, we can simply say that the high cutoff frequency is actually the bandwidth of your system. Okay. So I can write that the bandwidth with feedback is simply FHF, and FHF is FH multiplied with 1 plus beta A. Okay. So the gain bandwidth product AF multiplied with bandwidth with feedback will be simply A multiplied with FH multiplied with 1 plus beta A. This is your bandwidth. This is the gain. Okay. So if you look over here, 1 plus beta A, 1 plus beta A cancel out. So you left with A multiplied with FH. So if you have a feedback, the gain multiplied with bandwidth is equal to the gain without feedback. A multiplied with the high cutoff frequency. Okay. So meaning that the bandwidth, similarly, we assume that FL is much less than FH. The bandwidth is just FH. So the gain bandwidth product for amplifier without feedback will equals to the gain bandwidth product of the amplifier with feedback. So this is important because you have to look at the data sheet to find the overall gain or the gain without feedback. So with this information that the gain bandwidth product of the system with or without feedback is equal, you can find the bandwidth of the amplifier. So with that, I have covered 4 advantages of having a negative feedback. I will stop here first, and there is another one, advantages of having a negative feedback. That one I will continue in the next video.